Hello. Decided to show you a little video on formal charge and what formal charge can be used, how it can be used. So let's look at diphosphorus monosulfide. So let's look at the number of valence electrons. We know phosphorus has 5, so 2 times 5 plus sulfur has 6. So we have 16 valence electrons to work with. Let's draw the skeleton. We just subtracted 4, so we have 6 pairs left. Let's distribute those. 1, 2, 3, 4, 5, 6. And of course now we look at whether the octet rule is being satisfied. And we see that the central atom's fine, but the outside atoms are not. So what we can do is let's slide these two. See what I did there? Let's slide these 2 electrons there. Now the octet, this sulfur has the octet. That phosphorus is good. And so let's share these 2 in between the 2 phosphorus. So let's slide these 2 in between. So we have a Lewis dot structure. Now, who's to say phosphorus is in the center? So let's say sulfur's in the center. Let's draw a Lewis dot structure. It would, if we cut right to it, would look like this. So we can use formal charge to determine which of these structures is the correct one, or the one that's more prominent. So let's look at the formal charges of each of the atoms. So we look at phosphorus. We know phosphorus has 5 valence electrons. So we take 5 minus the number of bonds connected to it, 2, plus the number of dots, 1, 2, 3, 4, and we get minus 1. This central atom here, phosphorus, so we have 5 valence electrons. Phosphorus has 5 valence electrons. 5 minus 4, that'd be plus 1. And then the sulfur has 6 valence electrons, minus 2 bonds plus 4 dots, that's 0. So what we have here is this phosphorus has -1 formal charge, that phosphorus has a +1 formal charge. Total charge is 0, which makes sense. Hey, let's make sure you understand what equation I'm using to figure out formal charge. It's equal to number of valence electrons in the atom minus number of bonds plus number of dots. I think that's a pretty easy way to remember how to calculate formal charge. There's other equations you'd see written in textbooks or on other sites. So let's look at the formal charge here for these atoms in this compound. We know that phosphorus here has, it's 5 minus 1, 2, 3, 4, 5. So this is going to be 0. This is interesting. This sulfur has 6 valence electrons, and then minus 4 bonds. There's no dots attached to it. So this is actually plus 2. And then this one here, I'm sorry, I need to go back. That can't be 0, right? So 5 minus 2 minus 4 makes sense. Oh, excuse me, plus 4. That's -1. That's -1. Total charge is 0, so that makes sense. You can check yourself that way. And you see that these formal charges are higher, so this can be ruled out. So this is the correct structure for diphosphorus monosulfide. Let's try formic acid. Let me just draw 2 Lewis dot structures for formic acid. That you should recognize as being a formic acid. So one Lewis dot structure would look like this. And the other one, you could draw a Lewis dot structure that looked like this. You probably can tell right away which one we're going to rule out. But let's use formal charge to determine this hydrogen's good. This is 0. That's 0. This carbon, it has 4 valence electrons. 4 minus 4, this is 0, formal charge. This oxygen, 6 valence electrons. So it's 6 minus number of bonds plus dots. So that's 0 formal charge. And this oxygen is 0 formal charge. So we know that's going to be the good one. That's the correct Lewis dot structure for formic acid. Let's look at this one. Again, the hydrogens are 0. This oxygen here would be 6 minus number of bonds, 3, plus number of dots, 2. So this is plus 1. So right away, that rules out this structure. This here, can you figure out what the formal charge for this oxygen is? 6 minus 7. Yes, -1. It has to be -1, so it cancels out. So that's the winner. This is the winner. All right, formal charge. Let's go on to ozone. Ozone. Let's figure out the valence electrons. 3 times 6, so we've got 18. Let's draw the skeleton. -4. 14, that's 7. 1, 2, 3, 4, 5, 6, 7. Check the octet. We see that the central atom needs 2 more electrons to slide these 2 in between. Like that. All right, and that is ozone. Of course, there's a resonance structure that we'll need to draw for ozone. Since this really is not a double bond, that's not really a single bond, 1.5 bonds, 1.5 bonds. So the way we do that is we just draw the 2 extremes. All right, so let's see if we can find the formal charge for these atoms in this structure. We know the total charge has to be 0. Ozone doesn't have a charge. This oxygen, double bond, 2 lone pairs, 0. That's a 0 formal charge. This one, it's going to be 6 minus 3 plus 2. That's going to be plus 1. And this has to be -1 then, okay? So this oxygen has a formal charge of plus 1, -1. These are resonance structures. We don't rule any of these out. Okay, let me just erase this resonance structure and let's do one more compound, cyanide, right here, CN-1. So we have 4 plus 5 plus 1. That -1 means we add an electron. So we have 10 valence electrons to work with. We just used 2. We're down to 4 pairs. 1, 2, 3, 4. See what we're going to do? Yeah, we're going to slide, do the old slide, throw those 2 in here, throw those 2 in here, and let's put this lone pair here, this lone pair here. Now let's figure out the formal charge of the atoms. So this carbon is 4 minus 3 plus 2. That's going to be -1. Did I do that right? 4, 3 plus 2, it's -1, sure. And then this nitrogen is 5 minus 3 plus 2. So that's -1 as well. Now we need to go back to this. So I messed this up somehow. 4 minus 5 is -1. 1, 2, 3, 4, 5. That's right. And this guy's 5 minus 5 is 0. That's the mistake. So this is interesting. Reason this could help is cyanide is a conjugate base. So what this tells us is if there's a hydrogen ion hanging around, that it would bond here to the carbon. So formal charge can do a few things. Can rule out some structures. It can tell you the charge of the atoms in a structure. And then also, It can tell you maybe which side a hydrogen ion will attach to, in this case, this conjugate base. That's all. Formal charge. Thanks.